Hello and welcome to the fifth in a series of 6 films about the standard level equilibrium topic. Up until this point we've been looking at what equilibrium is and what Le Chatelier's principle tells us about how we can influence the position of equilibrium. In this film I suppose we're going to try and put ourselves in the shoes of an industrial chemist and ask ourselves the question of why it is that we might deliberately choose conditions of temperature and pressure that are not going to improve our yield. And in doing so, we're going to need to talk about what we mean by optimum conditions and what we mean by this thing called yield, which we've just mentioned. Now, up until this point, we've talked about how much of the reactants turn into products in terms of the position of equilibrium. So if we've got lots of reactants and not a lot of products, where the position of equilibrium is to the left, and if it's to the right, then it's the other way around. Okay? Now, an industrial chemist would say that if the position of equilibrium lies to the right, then they've got a high yield. Okay? Now, we might think that an industrial chemist would therefore say to themselves, okay, I'm going to choose the temperature and pressure that give me as much yield as possible. In other words, that pushes the position of equilibrium right over to the right-hand side. However, what they will often do is not choose the conditions that give them maximum yield, but try and optimize their conditions for yield and rate, and if we're lucky, for safety too. Right? So there's no point in producing lots and lots of product if it takes you years to do that, because you can't be selling it whilst you're making it. Okay? Similarly, if your plant keeps going bang and injuring your workers, then you're going to be paying out huge amounts of money in compensation, I suppose. So you want to do things in a safe way if possible as well. So you want to produce your product quickly, even if that means you don't produce huge amounts of it, and you want to do it safely. Now, if you think about what this means for you in your IB exam, then you're going to be trying to explain why the conditions that are chosen. And if you're going to be trying to refer to the yield, then you're going to be talking about Le Chatelier's principle. But if you want to be talking about rate, then you're going to need to refer to collision theory. So that's the kinetics topic that you've hopefully studied, right? And here, if you remember, we're talking about how often particles collide and whether they've got enough energy to react when they do collide. So it's an important thing to have an understanding of collision theory when we're trying to consider optimum conditions, because it's not just about equilibrium. Right, let's consider the sort of temperature that an industrial chemist might want to use. And in doing so, let's first of all look at a reaction that has a negative enthalpy change. And we should remember that that means that the forward reaction is exothermic. I'm focusing on the forward reaction here because really this is the one that we want to favour if we want a high yield. So we're going to look at things from a yield perspective and from a rate perspective, and we're going to ask ourselves, what sort of temperature would I ideally like to use? Okay, now if I want a high yield, I want to favour the forward reaction, which is exothermic, so it gets hot. So the system must be opposing what I'm doing by getting hot, so I have to use a low temperature to favour that forward reaction. However, what effect is that going to have on my rate? I have to ask myself. Okay, and collision theory tells me that if I use a low temperature, the particles will be moving slowly, they won't be colliding very often, and most importantly, they won't have a lot of energy when they do collide. So the rate is going to be low if I use a low temperature. So from a rate perspective, I'd like to use a high temperature. Now you can see there's a kind of conflict here. So what we're going to have to do is we're going to have to compromise on temperature. We're going to have to use a temperature that's high enough to give me a decent rate, but low enough to give me a decent yield. And we'll see in the next film what a sort of good compromise temperature might look like. Now, let's have a look at a situation where the enthalpy change is positive. Okay, and in this case we know that the forward reaction is endothermic, and think about what we would like to do in terms of the temperature if we want to maximize our yield and maximize our rate. In other words, to choose optimum conditions. So what temperature do I want? Okay, now in this case I want to favour the forward reaction, which is endothermic. It makes things get cold, so I want to use a high temperature. I'd also like to use a high temperature for the rate, as we've just discussed. Now here we've got an option of using a temperature of thousands of degrees centigrade, because we can really achieve very high temperatures these days. The trouble with that is that using a very high temperature is going to cost a lot of money, because you have to heat things up. So although in this particular case you might like to use a very high temperature, you're going to bear in mind the fact that using high temperatures costs a lot of money. So you're not going to go for thousands of degrees, you might go for hundreds. Okay? Let's move on and talk about the other sort of things that affect positions of equilibrium. And if you remember, they were concentration and pressure. I'm not going to look at concentration, I'm just going to look at pressure. Why is that? Well, that's because most of the industrial, or all of the industrial processes that we're going to study in this course involve gaseous reactants and products. So we're really going to be looking at pressure changes, not concentration changes so much. Let's start off by looking at this reaction here. And if you remember, when we're talking about Le Chatelier's principle and yield, or the position of equilibrium, with respect to pressure, then we need to consider how many moles of gas there are in the equation. And we can see here there's 1 mole on the left, although it doesn't say these are gases, I'm telling you they are. There's 1 mole of gas on the left and 2 moles on the right. So now again, if we ask ourselves, what sort of conditions would I like to have for rate and yield? What sort of pressure would I like to choose? Well, if we start off by talking about the yield and Le Chatelier's principle, remember we want to increase our value of K. We want to have a lot of products forming if our yield is going to be high, right? So in other words, we want to push our equilibrium over to the right, and there are more moles of gas on the right, so that's going to increase the pressure. So we must have lowered the pressure in order to get that to happen. So in order to get as much of our reactant to turn into products as possible, we want to use as low a pressure as possible. However, collision theory tells us that if we use a low pressure, there's not going to be a lot of particles per unit volume, and they won't collide very often. So from a rate perspective, we'd like to use a high pressure. And again, we've got this conflict here, so we're going to go for a compromise pressure. And once again, I'm going to get you to hang on until the next film so that you can see what sort of pressure we might be talking about when we say we're using a compromise pressure. Let's have a look now at this system where we've got 2 moles of gas on the left and 1 mole of gas on the right. And again, ask ourselves, what are we going to do if we want to get maximum yield? And what are we going to do if we want to get maximum rate? What pressure am I going to use? Okay, so we'd like to favour the forward reaction as usual for yield. This is going to reduce the pressure, so we want to use a high pressure to favour the yield. And as we've just discussed, rates also like high pressures. Does this mean that we're going to go for a pressure of thousands of atmospheres? Because we can achieve that. The trouble with doing that is if you want to build a plant that withstands very high pressures, you've got to use a lot of steel or whatever you're making your vessels out of, and so that's going to cost you a lot of money. Also, if you're running at very high pressures, there's an increased chance of accidents happening, and if things are going bang, then you're going to be spending a lot of money repairing stuff and possibly forking out for injuries to your workers, which we don't want. Okay, so although we're going to increase the pressure here, we're not going to go as high as we possibly can because we want to save money and we don't want things to be dangerous. Once again, we could consider the equilibrium constant here. I've put them in every case, but we don't really have to refer to the equilibrium constant here. It's just trying to get you to think about the fact that if you want to increase the yield, you want to increase the value of K, and you want this to be large. Anyway, lastly, let's have a look at something which I'm not going to look at in terms of collision theory. I'm just going to talk about what effect we might have on our yield by changing the amounts of reactants and products. Now, you might expect that an industrial chemist is going to want to remove their product sooner or later, right? What effect is that going to have on yield if you remove some C? Well, its concentration is going to drop or its pressure is going to drop. So the system is going to want to say, well, I'm going to want to increase that again, so it's going to push the equilibrium over to the right-hand side. So in fact, removing your product is good for your yield. It will turn more of your reactants into products. And if you've got some unused reactants and you pump them back into your system, then you're going to be increasing their concentration, and that's also going to push your position of equilibrium over to the right. So recycling your reactants and removing your products actually increases your yield, which is good. Anyway, hopefully you've got an understanding now of why industrial chemists choose the sort of conditions that they do based not only on the position of equilibrium but also on rates and safety. If you've got any questions, if any of that didn't make any sense, or if you've got any comments, please feel free to come and see me or to post a comment on YouTube.